is our CS3540 final project for machine learning. So our problem that we are attempting to find a good solution for falls under the umbrella of the field of speech emotional recognition, which is an important and a growing field within the machine learning community. There's been lots of previous work attempting to fix our main problem, which is being able to classify emotion from exclusively audio inputs. So from human speech, providing that a label for a predicted emotion. So this, like I said, is a really important field, has a lot of uses, like, for example, more nuanced information from transcription. So instead of just changing an audio input to text, it provides a little more of the human aspect to it with an emotional prediction. This can better or improve human-computer interaction. Whenever human speech is any sort of audio input, just provides more information for the computer so we can have a better communication between those. And this can also be a tool for the deaf and hard of hearing community, just to, like I said, provide some more information when it comes to human speech and those who have trouble reading emotions, especially in scenarios where body language or facial expressions might not be available. So just in general, the field of speech emotional recognition is just a way to help facilitate meaningful and inclusive communication, whether it be between humans or between a human and a computer. So our goal here was to create an accurate and robust emotional classifier that operates exclusively on audio inputs. So we're taking the audio inputs and trying to give them a emotional label and also an emotional intensity label. So Nathan, you can talk a little bit about our data that we used to tackle this problem.
All right. So we found our data set on the website Kaggle. This consists of 1,440 audio files that are spoken by 24 different voice actors. And each voice actor speaks in 60 different audio files that are each about 3 seconds long. The files in our data, the data is already labeled in the file names, and each file name consists of a 7-part numerical identifier that defines modality, voice channel, emotion, emotional intensity, statement, repetition, and actor. The files are spoken with one of with the emotions of neutral, calm, happy, sad, angry, fearful, disgust, or surprised, and they're spoken with intensity levels of normal and strong intensity. There are also 2 different statements. The dog is sitting by the door and the kids are talking by the door, and they're in each audio file uses one of those 2. So we have a couple example audio files. This first one is the fearful emotion with a normal intensity level.
Kids are talking by the door.
And the second one is the disgusted emotion with a strong intensity level.
Dogs are sitting by the door.
So first we need to extract the features from the audio files. We chose to do this with a Python package called OpenSmile, and this allowed us to generate features from the audio files pretty easily and fairly quickly. This gave us 88 features, and this included features such as MFCC and short-form Fourier transform features, which are pretty commonly used features from audio files, and it also and many other features. The way that this extraction gave us for each one audio file, it gave us 1 row in a new data set. We also have our 2 target features being emotion and emotional intensity, and we got those labels from the file names that we talked about previously. We also did not need any special hardware to process our data, and our no information rates are for emotion is a 12.5% rate because every emotion has a standard number of audio files in our data set, and for emotional intensity it is 53.5% because because the neutral emotion did not have a strong intensity level. It was just the normal intensity level. Eric, take it away.
For our trained test split, I apologize for talking over you. For our trained test splits, we decided to do 2 different splits, one without validation and one with. So the without validation was the 80-20 with the decision tree, random forest, and SVM, and the one with validation was 60-20-20 for the neural networks. Because of the way that our data is laid out with all the actors, we were worried the model might learn things about the specific data in the test set during training. So in order to prevent this, we made sure that rows from a specific actor were in a single partition of the data set. Next slide. Just the machine learning, as I said before, for the train test splits, the machine learning approaches we used were decision trees, random forest, SVM with PCA, and neural networks. So, Skylar.
Yeah, so for decision trees, we had an emotional accuracy of 31.66% and emotional intensity accuracy of 64.33%, both higher than the no information rates. But if you look at the confusion matrices, this is still not that great. For instance, in the bottom left with emotion, you can see there's a lot of incorrect predictions. The correct ones should be on that diagonal line, but you have a lot of other predictions there. Kind of looks like noise. But it's kind of concerning and tells you the model isn't actually doing that well. In the bottom right, you have the intensity confusion matrix. On the upper half of that, you have the true label of 1. And so it predicts that one fairly well. It's 126 to 34. But on the bottom, for the label of 2, it's 73 to 67. So it's actually incorrectly predicting that label more than it's getting it right, which is concerning. So then on to random forests. We have an emotional accuracy of 45.67% and emotional intensity accuracy of 77.67%, which is better than both the decision trees and the no information rates. In the bottom left, you can see there's a lot more of those emotions being correctly predicted along that diagonal, which is much better to see. It's not perfect, but it's definitely better. And then on the bottom right, you have the intensity confusion matrix. This one also performs much better. I mean, that upper half, the label of 1, that's correctly predicted most of the time. On the bottom, that true label of 2 is predicted wrong a bunch of the time, but it's at least predicted right more than it's wrong. So back to you, Eric.
For the PCAs, the SVM doesn't do well with large features, large amounts of features. So we use PCA to shrink them down. PCA did pretty well with our data set, achieving like a 50% variance with just 2 components. But so we had a goal variance of about 90%. So that shrunk our data set from 88 features to 20 components. Just to be able to look at a nice graph with the 2 components, you can see that the emotion isn't that great to look at. I mean, it's nice and pretty, but it doesn't really show us much. You can still see clumps of colors, but everything is kind of all mushed together. The intensity is a little bit better. You can see the normal versus strong. The strong tends to be more to the right, normal to the left, but there also still is a lot of intermingling in there.
So we took those 20 components from PCA and we used them in SVM, which we tried SVM first without those components and it performed pretty poorly. But with just 20 components, it was able to manage those a lot better. So we see in our emotion confusion matrix, it has this nice diagonal. It's still some noise on the outsides, but it's able to correctly predict those emotion labels with pretty good frequency. It had an accuracy of 51.33%, which is quite a bit better than our no information rate. And for intensity, we still had this problem, as you can see, where it's predicting a lot of 1s, but it was able to achieve an accuracy of 76%, which is also quite a bit better than the no information rate.
Our last machine learning method that we used was a neural network. And so we created a neural network for our emotional classification as well as our emotional intensity prediction. So a little bit about our structure. We used the Keras library from TensorFlow using Python to create our networks. And our network design for both was a fully connected network. As you can see with those dense layers. In general, when finding the best architecture for our use case, we experimented a lot, but found that more layers, deeper layers provided the best results. So for either case, so with our layers that we created, a couple things about them. So we use these dense layers that are fully connected. Our activation function that we chose was ReLU, or rectified linear unit. This to include some nonlinearity in our neural network, as well as have the most efficient computation time to cut down on this training time. Our final output layer, we use the softmax function, so we could get individual probabilities for each emotional label and emotional intensity label. So we used 50 epoch training for our emotional classification and for the emotional intensity. We also tried that 50 epoch, but we found a plateau with our validation loss. So we were kind of getting into that realm of overfitting. So we used early stopping to stop there, and we found pretty good results for that. Moreover, to combat overfitting, we added these dropout layers within each of our networks just to form as or have a form of regularization to make sure that we're not training too specifically to our training data and can still generalize pretty well. So Skylar, if you could talk a little bit about our results from our neural networks.
Yeah. So we had a 47.33% accuracy for emotion and a 77.33% accuracy for emotional intensity. On the bottom left, you can see you still have a lot of correct predictions for emotion along that diagonal. But there are a bunch of incorrect predictions for that second predicted label too, which is kind of, I mean, it's kind of concerning, but it's not the worst thing. Then over to emotional intensity, you actually have the same amount of the true label 1 predicted on that upper level, or like the top two boxes, being 141 and 19. And on the bottom, you still have a lot of that predicted label 0, which is actually 1. There's just some pre-processing that happened for this. And so it's that bottom section is basically a little like, it's not correctly predicting all the time. So on to the next slide, we have a bunch basically comparing all the confusion matrices. So you basically, for intensity, like SVM, random forest, and neural networks all do a pretty good job. They're all decently similar, which we'll see in a little bit with precision recall. And basically, decision tree is the only bad one. Then for the emotion confusion matrix, they're again all pretty good except for decision trees. If you want to pause and look more at these and compare them, feel free. We're running a little late on time, so back to you, Henry.
Yeah, like Skylar mentioned, we had some, here are our precision recall results. Like we said, SVM was probably the best model that we had in terms of precision and recall for our emotional classification, so detecting between those 8 emotions. And for emotional intensity, like you saw in the confusion matrices, all of our models had similar results, similar accuracies, except for decision trees, and had a similar problem with detecting that second strong emotional intensity category. So within the precision recall values, we see all pretty similar. Potentially some random variation causes the differences between the models. But between random forest, SVM, and neural networks, we were very happy with our ability to predict emotional intensity from just those audio inputs. So that was our project. Thank you for listening. If you have any questions, you could send us an email. We provide those there on that slide. But thank you.